So the next topic that we're going to talk about is the integrals involving parametric equations. So in single variable calculus, we derive the definite integral formula to calculate the area under the curve of a function y equal to f of x. What we did is that we partitioned the regions under the curve from a to b into multiple subintervals with equal width. In fact, we divide the interval into delta x equal to b minus a divided by n, for n is the number of subinterval or the number of rectangles that you want to approximate. And then we approximate the area under the curve using the sum of the area of the rectangle used in these approximations. That means in order to approximate the area under the curve, we're going to calculate the area of this rectangles and then take the sum of it. So the area is approximately equal to the sum of the height of the rectangle times the width, in this case the equal width, for I going from 1 to n. Again, for n is the number of subinterval that you want to divide, or the number of rectangles you want to use in this approximation. Okay, now in order to increase the accuracy of the approximations, what you did is that you let n go to infinity, or you increase the number of rectangles that you want to use in the approximations to infinity. And when you do that, you have a exact valuations of the area. So here the area become equal to limit as n go to infinity of the sum of f of x sub I times delta x for I going from 1 to n. Okay. Now in the next picture, we can see that the area under this curve can be approximated using two rectangles. So in this case, you can see it's a little bit different width, but in practice, usually we just use the equal width. But it's just for demonstrations of how things are going to be. So the area under the curve can be approximated using two rectangles. In this case, the area under the curve can be approximated using 10 rectangles. And in the last case, the area under the curve can be evaluated or approximated using 25 rectangles. So the more rectangles you want to fit into the approximations, the more accurate the area is going to be. And at the end, instead of working with limit of the summations or limit of the Riemann sum, what we do is we turn this complicated equations into, or we turn this complicated formula into something easier to manage. That is the definite integral. So we write this as the definite integral from a to b of f of x dx. So f of x sub I turn into f of x, which is the integrand, and delta x turn into dx to indicate that you want to evaluate the integral with respect to the x variable. Right. And also the width becomes very small, so instead of delta x, you turn that into dx, and you want to evaluate the area under the curve between a and b. But in this context, what we want to do is we want to find a formula to evaluate the area of a parametric curve. So we want to evaluate the area under a parametric curve. So the parametric curve is of the form x equal to x of t and y equal to y of t, for t is between a and b. So now what we do is we're going to modify the limit of the Riemann sums a little bit. So we're going to use rectangle again, right, to approximate the area under the parametric curve. but we're going to manipulate the formula so that instead of just x and y, we want to involve t in the formula. So here it goes. So first, we want to evaluate the area of the ith rectangle. So the area of the I rectangle. So a sub I is equal to f of x sub I times delta x. Again, remember in this case we want to say that delta x is going to be equal, is equal width. So now what I want to do is I want to rewrite delta x as the difference of two values of x. So this is equal to f of x sub I times x sub I minus x sub I minus 1. Right. Now again, we want to involve t in this calculations. Instead of just x sub I, now I want to write that as x sub I of t. Right? So it's involved the parametric, the parameter t. So here you have f of x sub I of t times x sub I of t minus x sub I minus 1 of t. Okay. So one more thing here. So you have f of x sub I of t. So instead of f of x sub I of t, you have over here the assumptions that y is equal to f of x. That is, you can turn the parametric equations into some formula that we know in terms of y equal to f of x. So now instead of f of x sub I of t, you rewrite this as y of x sub I of t. And then times x sub I of t minus x sub I minus 1 of t. You want to manipulate this formula a little bit more by multiplying divided by t sub I minus t sub I minus 1. So you want to see the difference in t. Right. Again, you want to involve the parameter t in the calculations. So this becomes y equal to x sub I of t times x sub I of t minus x sub I minus 1 of t divided by t sub I minus t sub I minus 1. So you multiply and divide it by the same term. Again, we want to see t involved in the calculations. Okay, so now this is just the evaluations of one rectangle. You want to do the approximations for the area under the parametric curve. So you're going to take the sum of all the area of the rectangle. So the area under the parametric curve is approximately calculated as, so you have A is approximately equal to the sum of y of x sub I of t times x sub I of t minus x sub I minus 1 of t divided by t sub I minus t sub I minus 1. Right, so I minus 1 is the subscript. Multiply with t sub I minus t sub I minus 1 for I going from 1 to n. Again, n is the number of rectangles that you want to use in the approximations. Now, to increase the accuracy of the approximations, to increase the accuracy of the approximation, what we want is you increase the number of rectangle used to infinity. In fact, what you do is you let n go to infinity, or take the limit as n go to infinity of these summations. Y of x sub I of t. Now instead of keep writing t sub I minus 1 or x sub I of t minus x sub I of t minus 1, what we do is we rewrite the numerator as delta x sub I and the denominator as delta t sub I. Multiply with delta t sub I. These are just notations to indicate the difference in x and the difference in t. Now, as you take n to infinity, the limit of this quotient becomes the derivative of x in terms of t. So a quick note here is that the limit of n, as n go to infinity, of delta x sub I of t over delta t sub I is going to go to x sub I of t prime. And instead of writing the limit of the Riemann sum, what you do is you rewrite this as the definite integral from a to b. And the area is equal to the definite integral from a to b of y of x of t times x prime of t dt. So this is the formula to calculate the area under the parametric curve, x equal to x of t and y equal to y of t. Okay, so now let's do some example. So example, we want to determine the area of the cycloid whose parametric curve is given by the equations x of t equal to t minus sine of t and y of t is equal to 1 minus cosine of t, where t is between 0 and 2 pi. Now, as you can see in the image, this is the graph of the cycloid, and it can go on forever from negative infinity to positive infinity, but I just graph and restrict the value of t, or the parameter t, between negative 6 pi to positive 6 pi. So in this example, we just evaluate the area of the cycloid from 0 to 2 pi. So that is, you want to evaluate this area, the area of this region only. Okay, and we already derived the formula to calculate the area involving the parametric curve. So the area A is equal to the integral from a to b of y of x of t times x prime of t dt. For y is equal to 1 minus cosine of t and x is equal to t minus sine of t, and a is equal to 0, b is equal to 2 pi, so the area becomes the integral from 0 to 2 pi of 1 minus cosine of t times the derivative of x of t, so you have 1 minus cosine of t again, dt. So you have 1 minus cosine of t. You can distribute this out to make the calculation, to make the evaluations of the integral a little bit easier. So this integral from 0 to 2 pi, you distribute everything out and you get 1 minus cosine of t minus cosine of t plus cosine squared of t dt. Okay, and the middle two terms, you can combine them together and you rewrite cosine squared of t. You learn in calculus too, when you evaluate cosine squared of t, it's not a straightforward calculation. You turn cosine squared of t into 1/2 times 1 plus cosine of 2t. That's a double angle formula. So this is equal to the integral from 0 to 2 pi of 1 minus 2 times cosine of t plus 1/2 times 1 plus cosine of 2t dt. And then we continue expanding everything out. And this is equal to the integral from 0 to 2 pi of 1 minus 2 times cosine of t plus 1/2 plus 1/2 times cosine of 2t dt. And you combine like terms, you get the integral from 0 to 2 pi of 3/2 minus 2 times cosine of t plus 1/2 times cosine of 2t dt. And then you, instead of one big integral, you break this down into multiple integrals. So the integral of a difference is difference of integrals. The integral of the sum is the sum of integrals. So this becomes the integral from 0 to 2 pi of 3/2 dt minus the integral from 0 to 2 pi of 2 cosine of t dt plus the integral from 0 to 2 pi of 1/2 cosine of 2t dt. So this integral is very simple to evaluate. Right, so I'm gonna just write down the answer here. So 3/2 t evaluate at 0 and 2 pi minus 2 times the antiderivative of cosine, which is sine of t. So again, the antiderivative of cosine of t is positive sine of t. Okay. Evaluate at 0 and 2 pi plus 1/2. So the antiderivative of cosine of 2t is 1/2 times positive sine of 2t. Evaluate at 0 and 2 pi. Now you just basically evaluate this function as 0 and 2 pi. You get 3/2 times 2 pi minus 0 minus 2 times sine of 2 pi minus sine of 0 plus 1/4 sine of 4 pi minus sine of 0. Okay. Now sine of multiple of pi will give you 0. So sine of 2 pi give you 0. Sine of 0 is 0. Sine of 4 pi is 0. And sine of 0 is also equal to 0. Therefore, you're left with just 3/2 times 2 pi, or 3 pi for that matter. And the unit in this case, of course, is unit square because you calculate the area under the curve. Now let's move on to another topic.